Another example of logistic growth. A population of 20 wapitis, in other words, American elk, are introduced into an Arctic tundra reserve. It is estimated that the carrying capacity of the reserve is 2,000 wapitis. After 5 years, the wapiti population has grown to 33. Assuming the population of wapitis follows a logistic growth model, find the population as a function of time. Again, give this a try before watching someone else do the problem and see if you can do it on your own. So let's see, what do we know? We know that P of 0 equals 20. We know that L equals 2,000. And we know that P of 5 equals 33. Okay. So if we're looking for P of t, we know that P of t is equal to L over 1 plus b times e raised to the negative kt. Well, we know L. We know L is 2,000. So why did I bother writing L? I'll just replace that with 2,000. We still need to figure out what b and k are. Those are unknown constants, but we do know that P of 0 equals 20. So 20 equals 2,000 over 1 plus b. Remember that when t equals 0, e to the 0 changes to a 1, and now we could do the multiply by 1 plus b, divide by 20. 2,000 divided by 20 is 100, so b equals 1 less than 100, which is 99. So that's one of the unknown constants known. So now we have P of t equals 2,000 over 1 plus 99, e raised to the negative kt. Now we're going to use the other initial value of P of 5 equals 33. We'll put a 33 for the population. And we're going to see a similar solving process here. This time we're going to plug in a t-value of 5, though, so negative 5k. That's not as pretty, right, because we still have the e. But we can still do the multiply by the denominator and divide by 33. We'll get 1 plus 99 e raised to the negative 5k equals 2,000 over 33. Unfortunately, that does not reduce. So we'll maybe leave that as 2,000 over 33 and just do all the algebra. So by all the algebra, I mean we'll subtract 1 from both sides of the equation, divide that by 99, and then take the natural log, and then divide by negative 5. So k is equal to that big old thing. And if you're interested in a decimal approximation of this k value, it will work out to be about 0.101. And I'm not very comfortable rounding this to 3 decimal places. I'm very concerned that an error, a rounding error in the exponent, is going to cause some serious rounding issues later on. So to be safer, you might want to carry that out 3 more decimal places to 473. To be even safer, in your calculator, just store the value as a variable and just recall it over and over again. In fact, if you have a calculator that can save it as the variable k, all the better. Again, you can just, instead of typing in the number, just type in k into your calculator every single time you need it. And that's what I'm going to do. Because I have k defined as equal to this, then that is, for here on out for this problem, the value of k, and I don't need to worry about the big messy thing. I'll just name it what it's named, which is k. So I'm just going to leave this as my final answer, and that will be perfectly acceptable, provided that I have some work shown as to what k is equal to somewhere on this problem. So again, if you feel like it, you can rewrite it by putting this gigantic mess into your exponent, or this crazy decimal into your exponent. But again, if it's defined somewhere, then use a more convenient name for it and be on your way. All right, find the maximum rate of growth of the population. Okay, do not take the derivative. This is not something that I would want you to try to do by taking the derivative. Use the fact that we know when the maximum rate of growth is. It happens when we have 1/2 the carrying capacity as our population. So this time it's not asking for the time like the last few questions were. This is just asking what is that maximum rate of growth. So we're trying to find that maximum dp dt value. Okay, so dp dt is equal to k times p times 1 minus p over L. And I could just write L here. Since L is a nice clean 2000, I'm going to go ahead and put 2000 here. But it would be fine if you just left it as L because we have defined L earlier in the problem. I am definitely going to leave the K, as I've already discussed. All right, so we know that that's dp dt for any population. So the maximum is going to be when we have a population of, I heard someone say it, 1,000. Good. So we're going to evaluate dp dt when p equals 1,000. So that's going to be k times 1,000 times 1 minus 1,000 over 2,000, which is 1/2. So 1 minus 1/2 is 1/2. Multiplying 1,000 by 1/2, we get 50, or 500 rather, and we're going to multiply that by k. Again, if you feel like it, you can actually multiply in your calculator. You have this value stored, I hope. So you can multiply 500 times k. Thought I had that written down. So, oh yeah, here it is. It is, this is probably a nicer answer, 50.736. That's perhaps a more useful answer. And let's remember that this actually has meaning. So maybe we can apply units to it. K, on the other hand, doesn't have units. That's a scale factor. But this is finding the rate of change of P over T. P represents the population of wapiti. So 50.76 wapitis per unit of time. Our time is measured in this problem in years. So that's the fastest rate of growth of our wapiti population. It didn't ask when that happened. It just asked what that maximum rate was. Alrighty. Oh, look at that. Now it's going to ask what time that maximum rate of growth of the population will occur. I think that we've done this problem each and every time we've seen a logistic growth problem. So this should be very familiar to you at this point. Where are we at? We have the population carrying capacity is 2,000, so we're going to set our population equal to 1,000 and solve for t. Remember that k is a big messy value that we know, so I'll just call it k for convenience. Again, 2,000 divided by 1,000. For these problems, we're always going to get a 2 here. Subtract the 2 from both sides. Subtract the 1 from both sides to get 1. Divide both sides by 99. Get rid of the e by natural logging. And then divide by negative k. And that will give us a t value that we're going to call m, actually. So I'll go ahead and say t equals m equals negative 1 over k times the natural log of 1 over 99. And since we have k stored in our calculator still, we can just type that into our calculator and get 45.284 years. That is the time when the population growth is at that 50 wapitis per year. And then an interesting final question here. I think it's interesting, if I do say so myself. What will the population be at time t equals 2m? So we're going to evaluate p at 2m. And you can use a calculator for this. And it might be surprising, after all of these crazy decimals, if you have everything stored perfectly in your calculator, you're not going to get a crazy decimal answer. You're going to get exactly 1,980 as the population at time t equals 2m. And that might make some sense when you think about the carrying capacity of 2,000 and the initial population of 20. So we started out 20 bigger than 0, and then m years later, we're halfway to our carrying capacity. So another m years looks like, and again, that's because we're right at the middle at m. In another m years, we're going to be 20 away from L on the underside of it. So that's kind of a nice little connection to make there.